All right. Well, good afternoon, good morning, good evening to anyone who's on. Uh, Thanks for joining. I'm Jeff Brenica. I'm at Colorado School of Mines, and this will be the first round of the ACERS Introduction to Electroceramics course. We'll just jump right in. So as you probably noticed, this is being recorded. Hopefully that's okay with everybody. So before we get too far, I just want to give you a little bit of background on what to expect. These slides are all available on the Dropbox link that you should have received. The focus here is going to be on live participation. So I want people to ask questions. That's going to be a heck of a lot more interesting for everybody involved and hopefully more valuable. But at the same time, the recordings will be available after the fact for anybody in case you missed something or you want to go back and make fun of some misstatement that I made or something. Overall, we're trying to cram a lot of things into a relatively short amount of time. It's going to be a broad overview of what I consider the most interesting and most useful electrical ceramics. We'll talk about the fundamentals and then get into a little bit about applications. But I also want it to be of value to all of you. And since I don't know who you are or what you're doing for the most part, I have some homework for you. So I want to know what it is you're interested in, and then we'll tweak things along the way. And so we can modify that as we go. We can also do that live. Whenever you ask questions, I'll do my best to answer as we go. The hope here is that the expectation is that we have people from a broad background, a lot of different levels of understanding of material science coming into this. So hopefully everybody has a little bit of a grasp of chemistry, physics, and math. We're not going to be doing a lot of homework equations or anything silly like that. But I also don't want you to be scared of seeing the periodic table or just the word thermodynamics. So those kinds of things. If any of this is confusing, jump in and ask along the way. So first homework, just send me an email. Let me know who you are, where you are, in terms of understanding and interests. So I can tweak this as we go. I don't want you to tell me any job secrets or anything like that. But I do want to know enough just to make sure this is relevant. So tell me what you're interested in, and hopefully we can modify the content along the way. So yeah, again, this is available on Dropbox if you want to just click on the link instead of writing it down or anything. All right. So some additional resources. There is no required textbook for this course. There's no reason to go out and buy anything. But these are valuable resources. These are the books that I will be pulling quite a bit of information from. So I've tried to cite any figures or anything like that I'm using along the way, but these are common ones. So if you have these available, great. If you don't, they're just really handy resources that you can look up at some point. And we'll be coming back to these. A lot of these are classics, like the Jaffe Jaffe Cookbook and Nye are 50 and 80 years old, something like that. But they're still really good resources. All right. So why do we care about electrical properties of materials in the first place? Well, it's the properties. We want to be able to use these properties, these fun properties, for something. So this is a classic table that I learned about when I was an undergrad and keep reusing over and over again because it just helps to point out all these fun relationships and phenomena that we can take advantage of in material science. So we've got coupling of electrical behavior with optical and thermal and mechanical and all these different intersections. I'm not going to go through the entire table by any means, but this is just a way to think about why we use materials in the first place, and hopefully get some ideas of fun phenomena that you might not have known existed. So triboluminescence, for example, you smash on something and get light out of it. That's kind of a cool thing that not many people are going to think of. There are a handful of minerals that do this. Wintergreen lifesavers do the same thing. So fun activities like that. We'll get into some of the phenomena associated with those, some basics as we go through this. So some examples of the kinds of materials that we're going to be talking about. So we'll be talking about insulators and semiconductors to kick things off, and then we'll gradually get more and more specific as we go. So we'll talk about conductors and even high temperature superconductors that are ceramics. Capacitors, because they are everywhere. Every one of your cell phones has somewhere between a few hundred and a few thousand multi-layer ceramic capacitors in them. We'll talk about piezoelectrics for resonators, for ultrasound, and then how ferroelectricity enables a lot of that. We'll get into varistors if we have time at the end, and optical and microwave responses as well. So hopefully this is the kind of stuff you're excited about and you're interested in. If not, then please send me that email and let me know what it is you are interested in, and we'll tweak it as we go. So, right. So again, just some example applications. I mentioned the materials that we're going to be looking at chemistry-wise. So we'll be looking at oxides, non-oxides, complex oxides, simple oxides, aluminum nitride, porcelain glasses, the elemental and compound semiconductors a little bit, and then we'll get into the more fun perovskites and expanded families thereof. So barium titanate, all the PZTs and all of their many relatives, PMNPT and the like. And then hopefully we'll get a chance to get into some optical materials and properties towards the end, and talk about quartz, lithium niobate, lithium tantalate, those kinds of things. Put zinc oxide and aluminum nitride there at the bottom. The Wurtzite ferroelectrics have really exploded lately, so I'm going to throw in some of those examples along the way, in addition to the classic perovskites. So, and again, please feel free to jump in and ask questions at any point. No, we haven't gotten to a whole lot of detail yet, but I want to make sure that everybody's on the same page in terms of the concepts, the nomenclature, the way that we're referring to things. So we're going to be talking about dielectrics. That's just anything that's an insulator. So we'll also get into some conductors, but for the most part, we're going to focus on insulators, because sustaining a field is what allows us to do some of these other fun phenomena. Yeah, Lyndon, did you have a question? I guess not. Just a heads up, I also have the chat open in case you prefer to type something in the chat, or you can unmute and ask along the way. So we will talk a lot about defects. And when I refer to defects primarily in this context, I'm going to be talking about point defects. So these will be vacancies, these will be substitutions, these will be interstitials, those kinds of things. Yes, porosity, pores are defects. Cracks are defects. That's really not what we're going to focus on for the majority of this course. We're going to be talking about point defects because of their impact on electrical and a little bit optical, but mostly electrical behavior and properties. So and diffusion and those kinds of things. So when I say defect, assume that I mean point defect, unless I start, the context says that I'm talking about a pore or something along those lines. And Madeline, it looks like someone is still in Teams trying to jump over. So.
Hi, yeah, I'm trying to hopefully send a chat to where I don't have to join. We'll see if that works. I'm so sorry for all the confusion.
No problem. That's the danger of using Outlook. It wants to default to Teams, even though everyone hates it. All right, so other concepts we'll be talking about a lot, polarization. So I'm not meaning political polarization here. I'm talking about the actual dipoles that develop within a material. So we'll get into that in a lot more detail, probably on Thursday. And then just some simple solid state physics. So we'll be talking about band diagrams very briefly and these kinds of things. I am not going to spend a lot of time on ceramics processing, because we could have an entire course just on how to make stuff, probably 10 courses. But I am going to point out a few pieces of the processing aspects that are crucial to the subsequent properties that we end up with. So, for example, with barium titanate, there's a large size effect in terms of the dielectric response. And so how does the processing that we go through affect the grain size that we end up in there, and therefore the properties? How does the processing atmosphere that we're using affect defect chemistry and those kinds of things? So I'll throw those in along the way. And then, yes, we're going to have a little bit of circuits. It'll be very simple, just RLC, so resistor, inductor, capacitor circuits. But in order to understand the electrical response, we need to know at least a little bit about very simple circuits. So we're not going to be so fancy that we're going to end up designing any sort of bridges or anything like that. But we do need to talk a little bit about circuits. When I'm talking about crystal structures and symmetry, so we'll get into this. That's actually where we're going to jump in today, right after we get through this intro portion. I am going to use the ceramics sort of convention rather than what you may hear from hardcore crystallographers or geologists or metallurgists or microscopists. So we're going to talk about crystal structures using their prototypes. So when I say perovskite, that's going to refer to the AbO3 sort of unit cell. That's based around the way that the ions are coordinated relative to one another. I'm not going to refer to structures in terms of just symmetry, because cubic only tells you one portion of it. Perovskite only tells you one portion of it. We need to be able to combine these to understand how that unit cell and how that symmetry relates to the properties. So we'll get into that in more detail. Just a heads up that that's the nomenclature I'm going to use. And then when we talk about phases and equilibrium, and everyone is having nightmares about going back to thermo, we're going to be talking about compounds and solid solutions. And just remember that a compound is a very specific chemistry. And then if there is a solid solution, that means that we can essentially alloy that, is another phrasing for it, where we can get mixtures, change the chemistry a little bit. We have random distribution of a certain set of cations within that same crystalline structure. And that would be a solid solution. And then composite is when we will have totally different phases that have some sort of an interface. And so we'll get into that a little bit more. But these kinds of concepts, if they're completely foreign to you, let me know and I can give you some more background. If this is ringing a bell, but you don't remember exactly what it was, don't worry, that's what we're going to be covering as we go. Kinetic hindrance, so not everything gets to thermodynamic equilibrium, and the eternal fight between thermo and kinetics is one of the aspects that we're going to be talking about as we go through different pieces. Energy wells, about those kind of barriers to reaching equilibrium. We will spend some time on tensors and matrices, and so you'll have some scary looking equations, but don't worry, they're really just more for reference than anything else. So we'll be talking about, for example, with piezoelectric coefficients, D33 and D15, and stiffness coefficients and things like that. Again, don't feel bad if those seem foreign to you right now. We'll get into that later, but just a heads up that that's coming. And then defect chemistry, this is the kind of nomenclature that we'll be using. So that first one will be an oxygen vacancy, and then a magnesium vacancy next to it, magnesium on aluminum site. We will go through the nomenclature for those again. Just wanted to throw this out there as to sort of set a baseline. All right, nobody's interrupted with questions yet, so hopefully we're all still on the same page. So let's jump in with symmetry. So why do we care about symmetry? The next 10 slides or so are going to be, to some people, super boring, and to some people, super exciting. But it's really important as a place to start because of Neumann's principle. So the reason we care about crystalline symmetry is that the symmetry elements of the property. So it's the properties that we care about. That's the whole reason that we made this material in the first place, is to be able to take advantage of its properties. And the symmetry of that property is going to depend upon the crystalline phase that we make it out of. And so we're going to talk for the majority of this class about crystalline ceramics. Every now and then we'll throw in a glass that we'll talk about as well. So I use the very broad definition of ceramics, in that it's an inorganic, non-metallic solid. So I include glasses under that umbrella. Most of what we're going to focus on for this course is going to be crystalline, but we'll throw in glasses every now and then, and I'll try to be clear about that as we go. But anyway, the reason that we care about symmetry, and the reason that we're going to spend so much time reviewing crystal structures and symmetry operations and those kinds of things, is because those are absolutely crucial to understanding how they impact the properties. So dielectric properties, ferroelectric properties, piezoelectric properties, all the fun stuff, even conductivity, depends very, very much on the symmetry of the individual unit cell. So just some quick demonstrations of symmetry. You've seen these in some flavor at some point in your life, whether you've taken a material science course or not. So one example, reflection. That's pretty easy. So you got the dotted line here, and we're going to be reflecting across that. So hopefully that one is relatively straightforward. You're just mirroring something on either side of a plane. Rotation, it's also simple in its own right. So in this case, the example is of a fourfold rotation. So we take this one item and then rotate it every 90 degrees. So it's called a four-fold rotation because it takes four steps to get back to the original. So these are the components that go into whatever symmetry that we're going to be dealing with in any unit cell. The next one is a little bit trickier because we're no longer limited just to two dimensions. So it's an inversion point. So if we look at that first comma, apostrophe, whatever you want to look at it, whatever you want to call it, we are going to invert it through a specific point in space. And so that means if it starts above the plane, it's actually going to go under the plane and flip. And so the solid is meant to represent above a plane where that the dot is, and then the hollow version of it is below the plane. And so this inversion is through a specific point. So it's somewhat similar to a mirror, except instead of being through a plane, it's through a point, and you get that, and you're basically turning it inside out along the way. Any questions on that one? It's easy to visualize once you get it. Sometimes it can be confusing along the way. All right. And so the last one, turns out that there's very rarely do we ever really worry about this roto inversion because there's only one of them that is unique. The rest of them you can build up with combinations of mirrors and rotations and inversions and things like that. But it is a symmetry operator that goes into the way that unit cells and crystallography is defined. So I just wanted to point it out here. So a roto inversion is where you rotate and invert all in one step. So the example that's shown here is yes. Lynn? Right. So in this case, you've got a threefold rotation plus an inversion all in one step. So you don't stop after just the rotation. You do rotation plus inversion and then do another rotation plus inversion. And that's just an example there. All right, so those are the components of symmetry that we're going to be dealing with. You can throw these together and come up with 32 different point groups. And basically what that means is a point group is if you define a point in space and then do a variety of these different rotations and inversions, every kind of periodicity that you're going to come up with will fall into one of these 32 options. So the reason we care about point groups, you'll notice there are also 230 space groups on there. Crystallographers love to memorize a longer list of space groups. The space group is basically you start with a point group and then you add a translation. The properties of a material depend upon the point groups. So because we care about properties, we're going to focus on point groups. Real crystallographers love the space groups, but from a property perspective, it doesn't matter. It matters which point group you belong to. So that's where we're going to focus our effort. Of those 32 point groups, and the diagram that's over here shows a subset of them, some of the more interesting lower symmetry ones. So triclinic, for example, up here in the top left, you see there's a dot there. There is 0. So the symmetry for that one is 1. And that means there are no symmetry operations at all. So you start with that dot and it doesn't go anywhere because there's no symmetry to be had. If we look at this other example 2, you start with a dot and that's a twofold rotation. So you can represent it in either of those nomenclatures. So we're not going to go through a great deal of detail with these. If anybody has questions, these are good resources that you can look up. What we're going to do is focus on how these different symmetry operations and the associated point groups affect properties, because that's what we care about. So 21 of those 32 point groups lack a center of symmetry. And so a center of symmetry is just, if there is a center of symmetry, then it doesn't matter which point in the crystal you pick out, then there's going to be an exact pair through an inversion point of that center of symmetry. So you could pick any arbitrary point within a centrosymmetric crystal, and there's going to be an exact duplicate through an inversion point from that point. So that can be a combination of inversion points and mirrors and rotations and all that kind of stuff. What it means is that if you start with that amount of symmetry and you stretch on it and you tweak it in whatever way, it's going to be symmetric again. And so because of that, that high symmetry means that you cannot support fun behavior like piezoelectricity and ferroelectricity. So of those that lack a center of symmetry, so that means that there's at least one direction where you can pick an arbitrary point and it does not have an inversion pair. That means that you can do fun things like stretch on the unit cell and it develops a dipole. So if you stretch on it, you end up with some of the positives going this way and some of the negatives going that way. And so you can take advantage of that for fun properties, as we're going to get into. So you'll see on the slide that 21 of those 32 lack a center of symmetry, but only 20 of them are piezoelectric. There's always an oddball that's the exception. Point group 432 ends up being, it does not have a center of symmetry, but by the time you combine all those different all those rotations, it ends up not being able to support piezoelectricity. So it's really only useful as an exception to this rule. I think there's only one crystal structure that I'm aware of, one mineral that has that point group. There may be others, but it's not something that's super useful. So we're going to focus on the 20 that are piezoelectric, and that means that they lack a center of symmetry. So symmetry is somehow broken. There are a bunch of different ways to do that, but symmetry is somehow broken within that unit cell. Of those 20, half of them are also polar. And we'll get into this in a lot more detail when we talk about ferroelectrics. But polarity just means that the crystal structure already has built in a separation between positive and negative charges. So if you've got a unit cell of some sort, just at equilibrium, it's the way it's set up. There is a positive end and a negative end. And there are a gazillion different ways to do that. But there are 10 point groups where that is baked into the unit cell, into the crystal structure. So we'll talk about those more as we go, because those are the ones that enable all sorts of other fun applications. So from ferroelectrics to pyroelectrics and other things. We will not get into too much detail about magnetic point groups and magnetic space groups, but know that once you start talking about magnetism, things get even more complicated, because each individual electron and its spin is going to add another degree of freedom. And so not because of the left and right spins, up and down spins, however you wanted to define them, that gives you added complexity. And so if we have time, we'll get to a little bit about how to leverage that for wireless communication kinds of applications, that lack of time reversal symmetry that comes with magnetism. We'll see where we go based on people's interests, though. All right, so that's a super fast overview of crystallographic symmetry. A convenient way of remembering this, a little Venn diagram. This is primarily referring to insulators, because those are the ones that can be piezoelectric. If you could technically have a piezoelectric that is conducting, but you can't sustain a field in a conductor. So it's kind of a non-issue. But if we start with all materials that are insulating, or at least potentially insulating, and eliminate the portion that are centrosymmetric, then we get the subset of those that are piezoelectric. So that's the 20 point groups that lack a center of symmetry. Half of those are pyroelectric, at least half of the point groups. And then there's the ferroelectrics. So you cannot tell just from crystallography if a material is ferroelectric or not. You can tell just from crystallography with no other information. If you know its point group, you know for sure whether it can be piezoelectric or not. You know for sure whether it can be pyroelectric or not. But in order to be ferroelectric, you actually have to experimentally switch the direction of the polarization. We'll get into that in more detail later on. But just keep in mind that the ferroelectric materials are an experimental subset of the polar materials, of the pyroelectrics. And so that requires that you can apply an electric field and switch the direction of that built-in polarization. If the material breaks down before you're able to switch that polarization. So if the energy barrier to get that polarization to change direction is so large that you actually get dielectric breakdown, so a lightning bolt going through the material before you can switch it, then that material is pyroelectric, but it's not ferroelectric. So you have to be able to experimentally switch it. It sounds like a pedantic point where it's just focused on terminology, but it ends up being very important in terms of the way things are way things are applied and what kinds of applications you can use these materials for. All right. There are other ways of looking at the crystallography when we start looking at unit cells. So the way that the atoms are actually arranged. Again, I'm not going to get into too much detail here, but just a reminder that the way that unit cells are described, you start with a lattice. A lattice is just an arbitrary grid of points in space, and then you throw on top of that some sort of basis, and that forms your crystal. So the lattice plus the basis equals the crystal, and so the crystal, we're going to pretend like it's an infinite solid with no defects in it. That's the starting point. And that's the way that we're going to end up defining the unit cells. And the unit cell is the smallest piece of that otherwise infinite crystal that has all the symmetry that we need to describe it. So you can come back to this one if you need to, but there are a variety of different ways of describing crystallography, depending on which background you're coming from. I just wanted to get everybody on the same page with the way that we're going to be talking about crystallography in this course. So depending on how we end up arranging these atoms, they can form different cubic lattices, different tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, and hexagonal options. These are the possible ways of arranging those atoms together. And so these Bravais lattices, there are 7 Bravais lattices, and that just defines the symmetry of that unit cell. So if it's cubic, surprise, it forms a cube. If it's tetragonal, that's basically a cube that's stretched a little bit in one direction. Orthorhombic, you've now distorted it in both directions. So all the angles are still 90. So it's still sort of like a box, but none of the sides of that box are the same size. Monoclinic is if you take one of those and then lean it over, because mono, single inclination, that just means that there's one angle that's leaning. Triclinic, everything is all goofy. You've got 3 angles that are leaning. And then the last 2, you switch from a 90-degree Cartesian sort of coordinate system to more of a hexagonal approach, because in some cases that ends up being simpler to describe. If people have any questions about this, please jump in and speak up. Again, these are more for reference than anything. We're going to be talking about cubic and tetragonal and orthorhombic and all these different Bravais lattices on top of the prototype crystal structures. So we'll talk about a tetragonal perovskite. We'll talk about a hexagonal wurtzite, these kinds of things as we go. Just wanted to have this available so you can look back in case you're confused about pieces. So I mentioned that I'm going to use the classic ceramist nomenclature. So when I say rock salt, I'm talking about the crystalline lattice that it is represented by sodium chloride. I'm not referring to sodium chloride itself necessarily. I'm referring to that lattice that it takes up. So this would be the cations are 6-fold coordinated. If they're anions, the anions are also 6-fold coordinated. And these are really commonly formed cubic structures. You can have tetragonal or other distortions of a rock salt structure, but it's fairly uncommon. So that's one example. Diamond cubic and zinc blende are basically the same thing, but do you have one atom or do you have multiple different atoms? So if you have a single atom, this would be silicon or diamond or things along those lines. Then you form these tetrahedral units that stack up into cubes that are high symmetry. And in this case, everything is tetrahedrally coordinated. So the silicon sitting in the middle of this tetrahedron has 4 other species around it. And if those are 4 other silicon atoms, then it's called the diamond cubic lattice. If those other atoms are zinc sulfide, for example, then it's going to be a zinc blende. So the underlying lattice is exactly the same. It's just a matter of whether you have 1 atom or 2 filling up those tetrahedral sites. Cubic boron nitride takes on this cubic form as well. Very, very similar to that is wurtzite. So again, you've got all of your cations are surrounded by 4 anions, and each anion is surrounded by 4 cations. So you can represent this in either way, with either the cation in the center of the tetrahedron or the anion in the center of the tetrahedron. It's completely arbitrary and essentially equivalent. The difference between Wurtzite and zinc blende is when you stack these layers of tetrahedra on top of each other, are they stacked A, B, just back and forth? That forms a Wurtzite structure, which ends up being polar. If you stack it A, B, C, so that they're essentially rotating around, I guess, you end up with a zinc blende cubic structure that is higher symmetry and non-polar. And so the chemistry can be exactly the same between these two, but the properties are massively different between whether it's a cubic zinc blende type of structure or a polar Wurtzite. And so we'll get into some more examples along the way of Wurtzite semiconductors like aluminum nitride. They are incredibly important because of their piezoelectric response. They're used in every one of your cell phones for communicating with the cell towers. And if they were the zinc blende structure, then they would be useless for that because they would have no piezoelectric response. However, from a semiconductor perspective, a lot of times the zinc blende format is preferred because you don't have the polarity. Yeah, I'll try to draw some more as I'm going along instead of just waving my hands. So sorry. So for the Wurtzite, this ends up being polar along this direction. In the cubic form, because it ends up the stacking of these different tetrahedra line up on top of one another in a different format. There's A, B, C. They end up being non-polar. So we'll get into this in more detail as we go. But yes, thanks for pointing out along the way in case you need any assistance with my gesturing. All right, so those are some examples of the crystal structures and prototypes that we'll be going through. Fluorite is another one that we'll see frequently. And fluorite is one example where, depending upon convention or just what you're feeling like that day, you can represent this crystal structure in either of two different manners. So this one here is starting with the anion, in this case fluorine, at the corner. This is the exact same crystal structure, but represented with the cation at the corner. And so they're completely identical, but they look different because of you've basically shifted the starting point over a little bit. So some people prefer one or the other. The point that I want to make on this one is that if you look at the anion-centric version, so this one over here, you can see that there are 4 cations. If you can imagine that cube, there are 8 centers of these sort of subcubes within the structure, and half of those are filled with cations. Hopefully you can imagine that in your head. So we see that they're the top 2 corners that are in the back and the front, the back left and the front right on the screen, and then on the bottom we've got the front left and the back right are filled, and their corresponding partners are empty. You cannot necessarily see that clearly when you represent it with this cation-centric one. But what you do see is there's this massive hole in the very center of that unit cell. That if you can see that there are 4 anions, the pink ones, in this representation. There are 4 anions in the center, and there's a big hole right in the center of those 4 where there's no cation. So that's equivalent to this gap over here. The reason that matters, we will talk later about some ion conductors, and that big gap makes it really easy for this fluorite unit cell. So this is not vacancies. These are the way that the unit cell is built, even when it's absolutely perfect with no defects. But they have those large interstitial sites that can accommodate additional ions, or they can assist in diffusion of vacancies or of ions because of that just built-in hole in the crystalline structure itself. So those kinds of things will be important as we go along. Any questions on the fluorite? If you haven't looked at these crystal structures before or looked at them in a while, it may take a little bit to try and wrap your head around what's going on there. But that's an important one to point out. All right, another example, the perovskite. We are going to spend a lot of time talking about perovskite examples. So barium titanate, PZTs, lead magnesium niobate, PMN, all these different examples. They're all based on the perovskite structure. And again, the perovskite structure is one that can be represented in either of two completely equivalent manners. So in this case, this center B site cation is the same as that center B site cation. And so it's just a matter of whether the person that was drawing the unit cell decided that they wanted the corner of the unit cell to sit where the B site is. So if you look at it as AbO3 perovskite, you can either center that unit cell on the A, or you can center it on the B. And because that B site, this gray one, is surrounded by 6 oxygens. In either case, it's surrounded by 6 oxygens. But that, because of the importance of that octahedral coordination, that's why these, I don't know if you can tell my drawing there, but that's why even in the B-centered version, people often complicate it further by throwing in those extra oxygens that are technically outside of that unit cell, because it's so important of the coordination of that B site cation. So one thing that's difficult to see from this representation is that A site cation, the orange one, is surrounded by 12 different oxygen. It doesn't have to be oxygen. 12 different anions, and so that's 12-fold coordination of that A site cation is a little bit easier to see in this other representation. So what defines the prototype crystal structure? It's not the symmetry. It's the coordination of the different ions. So in the perovskite, we have the A site cations, these orange ones, are coordinated. They're sitting in the center of, coordinated by 12 anions, in this case, the blue ones. The B site cation is the one that's sitting inside of an octahedron. So that's 6-fold coordination. So that's what defines that structure. It's not necessarily the symmetry, because we can throw different symmetries on top of these different prototype structures. And that's where the fun comes in once we start playing with that. One other crystal structure that's going to be really important, especially to magnetics, if we make it that far, is the spinel structure. And this one is gnarly. It has a whole bunch of a whole bunch of atoms in its unit cell. What is important about it is that 1/3 of the cation sites sit inside of an octahedron, and 2/3 of them sit inside of a tetrahedron. And why that matters is because the octahedron has a little bit more space, and is centrosymmetric, or it can be symmetric. By tuning the different cations that you throw into there, you can force one or the other to go into a tetrahedral site or into an octahedral site. And by doing that, you can end up tuning the way which electrons end up being paired or unpaired. So that's why this structure ends up being very, very important for ceramic magnets. So hopefully we'll have time to get to that towards the end of the class. But the spinel structure is super, super important for magnetic ceramics. And it ends up being a big, ugly unit cell with a lot of atoms in it. But the important part is that you can engineer which cations go into octahedral sites and which ones go into tetrahedral sites, and from that, then engineer the magnetic properties along the way. All right. So I mentioned that it's not just the orientation it's not just the prototype crystal structure that matters. It's the symmetry on top of that. So when I talk with my metallurgy colleagues, they like to refer to things as just cubic, period, or body-centered cubic, or face-centered cubic, or something along those lines. And that's great if you have a very, very simple chemical system or very simple symmetry. But the reason that we get all of these fun electrical properties that we're going to be talking about later is because we get to combine low symmetry with various different crystal structures. So the perovskite is one that we will keep coming back to as an example, because at you can have a high symmetry version of this perovskite. Usually this happens at high temperatures. So very often, the higher the temperature, the higher the symmetry. And the baseline reason for that is simply that you sort of the hand wavy version, you give the atoms more energy to wiggle around, and they're going to take up more space. And the more space they take up, the more likely they are to be at a lowest energy state with a high symmetry crystal structure. So usually the higher the temperature, the higher the symmetry of the unit cell. There are exceptions, of course, but most of the time, if you don't know anything else, the highest temperature is going to be the highest symmetry. So within this same perovskite unit cell, it can be very high symmetry cubic. You could also take that unit cell and stretch it vertically. In this case, vertically. You could do the exact same thing laying down on its side, and it would still be tetragonal, as long as you're only stretching one of those axes. If you stretch it along two different axes, you get orthorhombic. And if you take the corners and stretch them out, then you end up with rhombohedral. Those are just examples. It's also possible to have monoclinic, triclinic, all these others, but I didn't want to complicate things too far. So just remember that the Rave lattice, which is the shape, so that's the tetragonal, the orthorhombic, rhombohedral, cubic, whatever. That's one component. And then the prototype crystal structure, the way that the atoms are arranged relative to one another, is a complementary portion of that. So we have to have both to really know what we're talking about. All right. The reason that I use those examples is because barium titanate, our favorite example for perovskites, shows this rhombohedral, orthorhombic, tetragonal, and cubic series of phase transitions. So this is rhombohedral, orthorhombic, tetragonal, and cubic. So ROTC, nice and easy to remember. As you, let's say you center this material at high temperature, and as you're cooling it down around 100, 125 degrees C, it's going to go through a phase transition and go from cubic to tetragonal. And that's where you see if we're looking at the lattice parameters here, we have a single lattice parameter that describes the entire cubic unit cell, and then it splits into the long axis here, and then the shorter axes there. And then it goes through another phase transition and develops an orthorhombic symmetry. Does anybody see any problems with this plot, the way that it's shown? So we've got cubic has one lattice parameter, tetragonal has two, and then we have the average right here. How many should orthorhombic have? There are three unique axes to an orthorhombic unit cell. So there should actually be three different lattice parameters in there somewhere. And in this plot, they've only shown two, and then show an average in the middle. So apparently Walter Mertz, who published this in the first place, got very upset when people pointed that out to him. But just a historical note for you. And then we get to rhombohedral, and the rhombohedral unit cell really only has one lattice parameter, but then it's sort of canted along the 1, 1, 1 axis. So each one of the directions, each one of the lattice parameters is the same length, but now the angles are no longer 90. So just an example of how we can take the same exact crystal structure, the perovskite structure, and have it go through different polymorphic phase transitions. So we get different symmetries, but it's still the same underlying structure. So because of that, each one of these phase transitions is a first order phase transition. And you'll notice there's some hysteresis here. So that means that you're going to see a different phase transition temperature on heating versus cooling, because these are displacive phase transitions. There's no diffusion required. We just cool it down and it snaps into this lower symmetry phase, or we heat it back up and it goes into a higher symmetry phase. So because of that, there's going to be a little bit of hysteresis before you get enough energy to kick it into that next phase. All right. So this is another piece of homework. They can be destructive. So that's a great question. let's go back to these phase transitions. Lead titanate, which shows very, very similar response to barium titanate, actually has a 6%. So in barium titanate, that's around 1%. For lead titanate, that same transition is around 6%. And so 6% is a lot of strain for a brittle ceramic. So it's very, very, very difficult to make dense lead titanate that doesn't just fracture itself when it goes through that phase transition. So there's a lot of strain, a lot of stress associated with that. So yes, great question. If the strain is small enough, no problem. We will see later on, though, that this does lead to the way that the material accommodates that strain leads to domains. And so those domains end up being a really, really important contributor to the ferroelectric, the piezoelectric, and all sorts of other properties, optical properties as well. So great question. All right, one more piece of homework for you. And these homeworks are not meant for you to actually have to do things or submit anything. They're meant for you to think on your own about how this applies to what you're doing in your job or what you're interested in for this class. So why are you taking the class? These are meant to help you think about how it can relate to what you're doing day to day. So if you want to send these to me in an email, great. If you don't want to, no problem at all. But these, I'll have a few of these along the way to just give you something to think about to try and make this course more relevant to what you're doing. So in this case, I want you to think about different crystal structures and crystal systems. So those Bravais lattices, those are the crystal systems, and the point groups that are relevant to whatever it is you're doing. So are you in a job where you're making a certain product all the time? Are you in an R&D position where you're investigating a wide variety of different things? How does this symmetry and crystal structure discussion that we just went through, how does that relate to your particular job right now? Again, if you feel like emailing that to me, great. If not, no worries. All right, now it is time to apply an electric field. So this is where we actually get into the electronic ceramics portion. So in order to do this, we're going to have to talk a little bit about some circuits so that the people are familiar with the phrasing and the different different behaviors. Again, don't be too scared. So I'll start off with a simple equation. So this is resistivity. Rho is resistivity. Sigma is conductivity. They're just inverted. So it's pretty intuitive that if something is a good conductor, it's a bad insulator or a bad resistor. If it's a good resistor, it's a bad conductor. So they're just directly inverted to one another. I've thrown the units on here that are commonly used. So resistivity is often reported in ohm meters or ohm centimeters. Conductivity is in Siemens per meter, Siemens per centimeter, or my personal favorite, mho. So these are ohms. And a lot of people use mho, which is just ohm backwards for conductivity. That didn't make one of the standard SI units, but it's a common one that you'll run into. So it's one of my personal favorites just because they spell it backwards. So from this, if we're looking at resistance, so if you go in the lab and grab a fluke meter or something and measure a sample, you don't measure resistivity, you measure resistance. And so resistance is going to be the extrinsic portion. Resistivity is just the intrinsic representation of that. So it's scaled by the sample size. So R is rho L over A, and that just means the longer the sample, the higher the resistance. The smaller the cross-sectional area, the higher the resistance. So hopefully this is intuitive. If you have a big pipe, you can flow a bunch of water through it. The resistance is lower. If you have a big wire, you can flow a bunch of current through it. The resistance is lower. The longer that wire, the higher the resistance will be. Hopefully that all makes sense. So the way that we describe these in terms of internal material properties, though, is this NQ mu portion. And there are a variety of different ways that this can be represented. I like NQ and U but there are varieties of deviations from that, modifications of it. But what it boils down to is it's the number of carriers, so N, and it's the charge of each one of those carriers. So what we're really counting here for conductivity is how much charge is moving. So we need to know how many charges. We need to know how much charge each one of those carriers is carrying with it. So that might be electrons, it might be ions, whatever it is, it's going to be the charge of each one of those carriers. And then there's the mobility. So how easy is it for those carriers to move through the material? So if it's a metal, then how easy is it for those electrons to move through the lattice? If it's an oxygen ion conductor like yttrium stabilized zirconia, then how easy is it for those oxygen ions to hop through the lattice? Those kinds of things. So that's really what we care about when we talk about conductivity of a material. So conductivity is important if you want a conductor. It's important if you want an insulator. You need to know what the species are and how they're moving and where they're coming from. So what is it that's giving us this N? Why are there conducting species in there? What kind of species are they, and where are they moving? So maybe this is a battery, and we want to move lithium ions. We want a very high mobility for high conductivity battery. Maybe it's a capacitor, and we want it to be very low conductivity. So we want as few carriers as possible, and we want a very low mobility for the carriers that are there. So that's what we'll go through when we get into more detailed applications as we get there. So if we're talking about electrons, so for example, electrons that are moving through a metallic lattice, that mobility almost always decreases. So when I say almost always, there's probably an exception out there, but you can just think of it as always. Electron mobility will decrease as we increase temperature. And so the way that I think about this, I live in Colorado, so I ski as much as I can, which isn't as much as I would like to. But if I'm coming down the mountain and it gets warmer and the trees start moving, I'm going to bounce off of them. That's what's happening to the electrons as they're moving through the lattice. If you heat the material up, the lattice will wiggle, and the electrons that are trying to flow through it will bounce off of that lattice as it wiggles, and the mobility goes down. If you cool it down and keep the atoms where they are, then the electrons can flow through the lattice more easily. Ionic mobility is usually the opposite. So ionic mobility can also undergo scattering from the lattice. So these would be, for example, oxygen ions that are moving through YSZ, lithium ions that are moving through a battery electrolyte. But because ions are much heavier, it's much more common for the ionic mobility to be dominated by the amount of energy available to get those ions to hop to the next spot. So electrons are sort of flowing in the superhighway of this lattice and bouncing off of the lattice as it moves. The ions themselves have to hop from one site to the next. And so when you increase temperature, you give those ions a little bit more energy to hop to the next site, and you allow them to hop more frequently. So if we look at temperature dependence of mobility, electronic carrier mobility will go down as we increase temperature. Ionic mobility will go up as we increase temperature, because you're giving those ions that are moving more energy to hop around. Great question. What would a material do if you have both? So that's actually one of the clever ways that you can identify how much of each you might have. So let's say you have, pick your favorite chemistry. You've got a material that has electrons and it has, let's say, lithium ions that are moving under a field. You apply a field and the electrons go this way, the lithium ions go that way, because the lithium ions are positively charged, electrons are negatively charged. How do you know which one is which? So one possibility is you set up electrodes where lithium is not welcome. So lithium can't go through that certain electrode. So it's called lithium blocking. And then you can say, all right, anything after I pile up lithiums up against this barrier, then anything else that gets through, that's got to be an electron. So that's one possibility. Another is that you just measure the temperature dependence. And so if you've got one contribution that goes up with temperature, another contribution that goes down with temperature, then you can balance those out or separate those two. We'll get into frequency dependence more in a little bit when we talk about alternating current, but that's another way, because if you have high mobility, then it's going to respond faster. So you can move things with a higher mobility, usually at a higher frequency. And so if you measure the behavior as a function of temperature and a function of frequency, then very often you can separate out different contributions like this. All right. Oh, and the Q. So this is the charge of each one of the carriers. We kind of ignore that one because the only time that ever changes is when you change the species. So if we're talking about electrons, it's always one electronic charge. If we're talking about oxygen vacancies, it's always twice the electronic charge, because an oxygen vacancy is an equivalent +2 charge. If it's a lithium ion, it's going to be a lithium +1. So unless we change the species that is conducting, Q is always going to stay the same. What about N though? Can we change the number of carriers? That's where we get to take a little detour into statistical mechanics. So again, for metals, this N is going to be constant with temperature, roughly constant with temperature. It changes a little bit, but not enough to matter. With ceramics, this can increase dramatically. So let's think for a second about how much. So orders of magnitude of conductivity. For electrical conductivity, we can change the electrical conductivity of a material by 40 orders of magnitude. That's 40 powers of 10. That is an insanely large range of values that we can have for electrical conductivity. To put that in perspective, if we think about a very closely analogous thermal conductivity. So you think about a really good thermal conductor, a metal pipe that you grab onto and it feels cold because it sucks all the heat out of your hand, versus insulation in a furnace or fiberglass in your attic, something like that, with very, very low thermal conductivity. Those can vary by maybe 3 orders of magnitude, 5 if you're really lucky. Electrical conductivity can change by 40 orders of magnitude. And that is because of this N right here. We can change the number of carriers dramatically. And that's why it's so broad range. And that's one of the fun things about electrical properties, in my opinion. All right, so this quick detour into statistical mechanics. So if you ever had to take a graduate thermo class, you learned this stuff. Don't worry if you didn't want to do that, because we're not going to get into detail, but I want to show you just enough so that you understand where these come from. Don't worry, no homework on doing quantum mechanics calculations or anything like that. So the way that we describe the number of particles, and these particles, they can be gas particles, they can be electrons, they can be anything. We're talking about this specifically for electrons in electrical ceramics and conductors or insulators, but you can use the exact same math for helium ions in a balloon, or helium atoms in a balloon, or whatever else you want. The point is, we're going to describe the number of these particles within a given range. So that DE just means, all right, I want to know within this range, or within this range here, or within this range here. What is the number of particles that have this certain energy within it, plus or minus a small amount. And so it starts out with this distribution and density of states. And the density of states is the same no matter which kind of particle we're talking about. But the distribution function is the part that varies with the kind of particle that we're going to be describing. So density of states is the same no matter what. Whether we're talking about photons or gas molecules or electrons, that's what tells us which one of these other distributions that we have to use to describe that. And so we're very briefly going to talk about these. The one that matters the most for electrons ends up being Fermi-Dirac. Maxwell-Boltzmann is the most generic. So this is same kind of statistics that you use for those helium atoms in your balloon. They're the same ones that you'd use for electrons at very, very high temperatures. Anything that where the particles are not going to be interacting with much, if it's very, very dilute point defects within a solid, then this is the kind of statistical approach that you use. Bose-Einstein is what we use for photons and other bosons. The key there is that they can occupy the same energy state. So you can have two different photons that are completely identical. They occupy the same energy state and they don't interfere with each other. That's what makes it a Bose-Einstein or a boson, which follows Bose-Einstein statistics. So if you've ever heard of Bose-Einstein condensates, so with all of the talk about quantum computing now, there's a lot of interest in looking at trapped ions and Bose-Einstein condensates at very, very low temperatures. You can actually get atoms to settle into the same energy state at low enough temperatures and form a Bose-Einstein condensate where a collection of atoms behaves as a single entity. So that's for the crazy low temperature physicists to deal with. What we're going to be talking about for the most part are electrons in a solid, and those follow Fermi-Dirac statistics. I'm not going to worry about the details of the equation, but I do want to point out that the form of the distribution, because this is really, really important to conductivity within these materials. So primarily within ceramics, this is the basis of the entire semiconductor industry. So these the Fermi-Dirac statistics are what apply to fermions. So that's electrons, it's holes, it's basically anything that obeys the Pauli exclusion principle. And so if you've heard of that, great. If you haven't, you probably had to deal with it in chemistry, whether you knew it or not. So if you went through in chemistry at some point and you drew the electron configurations where you said, here's the electrons, and there's some that are pointing up and some that are pointing down, and then there's unpaired ones. This is Hund's rule saying that you can only have electrons in certain energy states, and the only way that they can have sit in the same energy well is if they have opposite spins. That's just a reflection of the Pauli exclusion principle. And so these are the statistics that we're going to use to describe electrons within a solid. And the key here is that we've got a certain distribution, and at 0 Kelvin, at absolute zero temperature, all of the electrons are hanging out in their ground state, exactly where they're at their lowest energy state, because there's no thermal energy around to disrupt them. And so you can describe their distribution as this step function. So all of the electrons are in their lowest state. None of them are in an elevated state in any way. As you heat up the material, thermal energy is going to broaden this distribution. So at 293 Kelvin, that's the red one. And unfortunately, because this is for a fairly large bandgap, you can't see a heck of a lot. But when you get up to 2000 C, you can see that there's a broadening of this distribution. So instead of being a complete step function, now you've got a broader distribution. And what happened is that some of the electrons that used to live here, so this is the number of electrons that are in these different states. So the same number of electrons that used to live here are now hanging out at higher energy because they have that thermal energy to bump them up to a higher state. But you'll notice this center point is always the same. So regardless of the temperature, this midpoint is not going to change. That's exactly the same regardless of what the temperature is. We just change how many of the low energy electrons moved up into higher energy states. And so that distribution is always symmetric for a perfect material. So all that's saying is that as we heat up this material, you've got electrons that are jumping into higher energy states, and they're leaving behind holes that were in lower energy states. So seems fairly straightforward from a distribution perspective, as long as you don't have to go through the math. That pivot point right here is that Fermi energy. And you can see the KT is what says that it's dependent upon temperature. And so if we have a semiconductor or any sort of insulator that has a band gap, so all that means is that you've got this same exact distribution as before. The math stays the same, But suddenly we've got a region inside of that distribution where there are no energy states available. The distribution function says there should be electrons here, but there's no energy states for them to live. And so you end up with this gap that doesn't allow any energy states within that gap. So you've probably seen this kind of plot turned on its side. And you've seen it represented as a valence band and a conduction band with the Fermi level in between. And so these are at 0 Kelvin. These are all the electrons that are hanging out in the valence band at their lowest energy state. And there's not enough energy for any of them to exist up here in the conduction band. So there's no electrons in the conduction band in this example. We still have that same Fermi energy, same Fermi level, which is right here. So that's that sort of pivot point around which the distribution is going to distribute. As we heat things up, we're going to get a few more electrons that are populating these higher energy states, and they're leaving behind holes in those lower energy states. And so when we get to high enough temperatures, these electrons have enough thermal energy to jump across that band gap and populate the conduction band. And that's just represented with this population. So the Fermi-Dirac statistics, all it is telling you, here's where the electrons are going to live based on the temperature and the Fermi level, the energy of that gap. That's all we're worried about. So as we heat things up, we can change the number of electrons that are available in that conduction band. And so, as you can probably guess from the name, it's the electrons in the conduction band that actually lead to conductivity. So this material with a bunch of electrons in the conduction band is going to be far more conductive than this one that doesn't have any in the conduction band. And so if we go back to this earlier equation, all the way back, this N is entirely dependent upon that Fermi-Dirac distribution of electrons. And so if we're going to change the number of carriers with temperature, it changes by this factor. And it's that exponential dependence on temperature that is so important, because that's what means that the higher temperature we get, the more electrons we have available in the conduction band, and the higher the conductivity, because we pushed that N up. Now remember, we're changing, if we're going to change the conductivity by 40 orders of magnitude, that means we have to change the number of carriers by 40 orders of magnitude. So that's actually possible. Maybe not 40 within just a semiconductor, but we can change the number of electrons available in the conduction band by massive amounts, just by heating it up. And that's what's meant to be represented by these cartoons. Another possibility is if we throw in some sort of a donor dopant that is going to live within the conduction band. And so if we dope this material with something, so in silicon, for example, we might put in phosphorus that's going to provide an extra electron. So silicon has 4 electrons, phosphorus has 5 available, and so it's going to have more electrons that are contributed to the lattice. What that does is essentially shift the Fermi level up closer to the conduction band. And so all you're doing is shifting this distribution. So if you notice, the distribution went from centered around the Fermi level, the band gap is centered around the Fermi level, to now if we dope it, we have essentially shifted the Fermi level up within that band gap. So the band gap stays the same, we shift the Fermi level up. And because of that, it takes less energy for electrons to hop into that conduction band. And so then we can control the conductivity of these semiconductors, not just by temperature, but by putting in a bunch of electrons that are easily available at room temperature. And then if we do it right, then we have a large barrier for any of these electrons to hop up, because we want to be able to control things by the dopant, not just by temperature. Because if we want the temperature, if we want the conductivity to be the same or stable with temperature, then we want to be able to control that by doping rather than just by whether or not I walked outside on a cold day or went into a warm room. I don't want the conductivity of my device to change just by moving around. So that's a super simple overview of the way that semiconductor conductivity control works. If we look at what that means in terms of just comparing different materials and their temperature dependence of conductivity. So this is what I alluded to earlier, that for generic metals, we're going to see a decrease, a slow decrease in conductivity as we increase temperature. And that's totally dominated by this mobility term. So as the temperature increases, mobility decreases. That's because the lattice is moving around, the trees are moving around as the electrons are trying to ski. If we have a conductive ceramic like lanthanum nickelate or metallic YBCO or several other options that has a lot of electrons already populated in the conduction band, they can behave just like metals. So if you have something that is where the population of carriers, the N, is already set, then that will also show a gradual decrease as temperature goes up because it's going to be dominant. You're not going to change the N very much with temperature, but you will change the mobility. So how much is too much for the dopant? It's essentially linear. So you're changing, if you put in a dopant, well, it depends on the kind of dopant and the way it's compensated. So we'll get into defect chemistry later on. Let's say everything is ideal and perfect within a semiconductor. For every phosphorus that I put into silicon, I'm going to get one electron. And so if I want to increase this conductivity by 10 to the 18th electrons over what I had before, then I put in 10 to the 18th electrons in the volume that I care about. So it's essentially 1-to-1 for absolute perfect doping within a semiconductor. When we start talking about more complex materials, so we'll get to doping PZT later on as one example, we can have multiple different compensation mechanisms. So we might not just add an electron for every donor dopant that we contribute. It might be compensated in other ways. So to first approximation, yeah, every donor you throw in, you get a free electron. But there are always different mechanisms possible. So that really only applies for pure semiconductors. If we have a very wide bandgap semiconductor, so getting back to the conductivity part, for something where the number of carriers is what dominates the temperature dependence. If we have a wide bandgap semiconductor down here, that basically means this barrier is so large that it takes really high temperatures before we start to get any significant contribution to conduction. And so this whole region down here, we're only getting one electron hopping over the barrier. We get one more electron, we get one more electron, and finally we get to the point where that the 1 over the exponent of 1 over T, so we get the temperature activation of carriers is finally starting to take off. But for a wide bandgap semiconductor, that may take several hundred degrees C, or 1,000 C, or 1,500 C, or who knows, depending on the bandgap. You can calculate that from the Fermi-Dirac distribution if you care. For a smaller bandgap semiconductor, though, then we're going to see the same behavior, but it's going to start at a lower temperature because we get to temperatures where we're able to hop across that bandgap at lower temperatures, and eventually it starts to saturate. So we've gotten up here where so many electrons have hopped across that we don't have any more to contribute, and then it's going to start to saturate. That can happen. So essentially at this point, it's behaving like a metal because we've already thermally activated as many of the carriers as we're going to. So for conductive ceramic here, the schematic, the little cartoon that I've drawn, it would essentially be the same for any electronic or hole conductor. So as long as it's a high mobility electronic species. So for this, yes, I mean electrons or holes are the dominant carrier. And the reason for that is that those are going to be scattering dominated rather than hopping dominated. So if we're talking about an ion conductor, then that is going to increase a lot with temperature because we're going to have much more, even if the number of species doesn't change a lot, the hopping mobility will change. And I guess it won't bend up quite as much as that. It'll be much more linear. It'll be something along those lines. So because we're this would be for ionic hopping. Because we're increasing the mobility of the ionic species as we heat things up. So what would these look like with multiple conduction mechanisms? Shannon, you always ask the hard questions. It's going to be essentially a linear stacking of them. So if you, as I mentioned before, if you've got multiple different species that are occurring at the same time, you can separate them by, for example, doing measurements at different temperatures and seeing if you had an example where maybe at high temperature, as you increase temperature, the conductivity goes up, and then after a while it sort of plateaus and starts to drop off. That's saying here you're increasing the number of carriers, and here you are decreasing the mobility. So you might be in a regime where you're changing the species. You might be in a regime where you're completely you're just changing which is the dominant factor in those. So in this case, for example, you might saturate the number of electrons that you have available, which is sort of what's happening in that undoped semiconductor, the one in the blue. So another example, if you've got a handful of electrons, but not a huge number, you'll see this kind of behavior. And then you get to a point where you start to activate ionic conductivity, for example, but you've not gotten to the point where you're going to have a lot of electronic carriers. So one example of this would be yttrium stabilized zirconia. It is a very good electronic insulator and a very high ionic conductor, but you have to get to a high enough temperature for those ions to move. So at low temperature, it's going to look, I'll draw it on the open section over here. You're going to have a little bit of electronic contribution, and then you're going to get to the point where the ions are able to move, and that's exaggerating a little bit. So maybe the ions are starting to move, and then you get to the point where you've got an electronic species, and then they saturate out. So there are a bunch of different possibilities depending on the populations and the activation energies for each of these. But each one of them individually is going to contribute according to this general equation. Not exactly. So ionic conduction, the basis for skull melting of zirconia. So if anyone is not familiar with skull melting of zirconia, basically what you do is you heat up a hunk of zirconia and you use its own self as its crucible. So the reason that works is you're basically losing energy from the surface, and the surface is going to be cooler than the center. And so that means that the surface can stay at just below the melting point, and it can stay solid, and inside you can have a little bit higher heat capacity, or a little bit higher heat within the center, and that stays molten. And that way you don't have to have a crucible that is going to be able to contain the zirconia, because having something that holds molten zirconia at 2400 C or something along those lines is not an easy thing to do. But you have to get the center of it hot enough somehow in the first place. So we can come back to that one a little bit when we are talking processing later on, if you're interested. But in that case, it's not actually the ion conductivity that's contributing a heck of a lot for that one. All right. So just some other examples of materials and their various different conductivities. And note on this plot, this came from Carter and Norton's textbook. This is 1/T. It's actually 1000/T. So these are the opposite axis of what I've drawn here. But you can see that there's a very strong temperature dependence to some of these materials. These examples up here, so titania, TiO, rhenium oxide, these are metallic type conductors. So these are samples that already have a lot of available electrons. So as we're heating up, so this is actually increasing temperature. They're mobility dominated, so the overall conductivity is decreasing because the number of carriers isn't changing. It's just you're decreasing the mobility as you heat things up. On the other hand, you've got these that are very, very strongly temperature dependent, and that basically means that as you get hotter, you're activating more and more and more and more electronic carriers that are contributing, and that's why you get such a very, very steep contribution to conductivity. These are fun examples. These stair steps are examples of phase transitions. So you actually go through a metal to insulator transition. So at low temperatures, it's behaving like an insulator, and then you go through a phase transition and it becomes metallic, and now you've got a lot of free carriers that are available, and from then on it ends up being mobility dominated, and as you continue to increase, the conductivity reduces a little bit because of that reduction in mobility. And so vanadium oxide is one example of this. There are companies, for example, that are taking advantage of this phase transition. So if you've got an insulator, it's transparent. If you've got a conductor, it's metallic and it's going to reflect photons. And so you can make a window that is reflective at high temperatures, and then it cools down and goes through this phase transition and becomes an insulator and allows light to pass through. So you've got a window on your house that when the house gets hot, the window itself gets warm enough that the coating goes through a phase transition and becomes reflective and reflects away additional sunlight. So it stops heating up. And you've reflected enough sunlight, then your house gradually cools down a little bit and it goes through that phase transition, and now it's transparent again and lets the sunlight in. The challenge with that one is that the native temperature for that phase transition is about 150 C, I believe, 170 C, something like that. It's too hot to be useful for residential windows, but people are doping this vanadium with niobium or other materials to shift that phase transition to lower temperature. So you can have a completely passive window that regulates the temperature in your house just by letting how much sunlight, by adjusting how much sunlight is coming in based on the temperature itself. All right. Very briefly, just before we wrap up here, I want to talk about interfaces and junctions. We are not going to go into deep semiconductor physics here, but when we talk about varistors, we're going to need to remember some of this. So I want to just show you some examples while we're talking about semiconductors, that if you take an N-type semiconductor, so that's one that's donor doped. So this is donor doped, and this is acceptor doped, and we will use that terminology again later when we're talking about defect chemistry. If we take something that we intentionally put in extra electrons, that makes it donor doped, that moved the Fermi level up over here, we put in acceptors, which don't have enough electrons, so they steal electrons from the surroundings. That shifts the Fermi level down. And now we smash these two materials together. The Fermi level is going to line up. So that basically means that the electrons are going to flow until they essentially equalize their potential. And so on one side, you're going to have electrons that are freely available within the conduction band. Over here, you're going to have holes that are available within the valence band, but not very many electrons up in the conduction band. And so these kinds of junctions are the origin of all the fun stuff that we do in the semiconductor world to be able to make devices. And another example of this is a Schottky barrier. And again, we're going to use this when we talk about varistors. But a Schottky barrier is one. In this case, we're showing it in the example as a metal. So in a metal, the electrons go and there's no band gap. The electrons go all the way up to the Fermi level. And so when you do the same sort of scenario, you smash this metal up against a semiconductor, the Fermi levels are going to align and the vacuum level aligns. And if you've got a semiconductor here, this Fermi level, if you remember what the Fermi level represents, it is the midpoint on that statistical distribution. So it's basically the average. It's the middle of the energy distribution. So it always has to be at the center. And so when you smash this up against a metal, the bands actually have to bend to accommodate that. And so you end up with this little pointy barrier that is going to get in the way of electrons trying to flow. So we will take advantage of that when we start talking about varistors in a few more classes. All right, just a couple of minutes left. Any questions that people haven't yet thrown into the chat? All right, if you we will jump back in here on Thursday, and I will tweak things along the way based on the emails that you send me with your specific areas of interest. Any other questions that you have along the way, please don't be afraid to shoot me an email or save it for the chat during the next class. There are no other questions. Then thanks everybody for joining. Sorry for the confusion with the Teams link. Hopefully we got that all straightened out. But yeah, we will continue on. The slides are available if you want to look through them ahead of time and come up with some questions. Great. I look forward to talking with you on Thursday. Thanks.
Thank you.